In section 3.5, what we're going to do is we're going to take the concept of two variable equations, right? Equations given in x and y, and how they represent linear functions and lines, and we're going to look at systems of those. So the system is a set of two equations with two variables, or three equations with three variables, etc., etc. Four equations, four variables. Generally speaking, though, to solve a system, you need to have the same amount of equations as you have variables in order to solve a system. Okay? Let's go right into it. Three graphical representations. Okay? What I just talked about is pretty much what you're seeing at the top there. Now, three representations. If two functions are different from one another, okay, if they're different functions and they're not parallel, they have to intersect at some point. Any two lines that are not parallel, that are not the same line, will intersect at one point. It does not matter. It does not matter what the slope is. Even if it looks like they're not going to meet in the beginning, they will meet eventually over time. So if I have a line that looks like this, and this line is exactly parallel, yeah, they're not going to meet. But if I do this, watch, I just change it like that, they will meet eventually. Maybe, 1,000 feet in space, they will meet up, these two lines that are just not parallel. But they will meet at some point in time. So two non-parallel lines that are different from one another will meet with one intersection. The intersection is the solution to that system of equations. So for example, this is a complete hypothetical, I'm making up equations. This one might be y equals negative 3/2 x plus 5. Let's say that's the blue one. And the green line is y equals, it looks like these, no, they're not perpendicular. If they were, I would use 2/3. Let's say this is 1/2 x plus 3. Those two lines are completely different. They are not the same line. We can clearly see that. We also know that they're not parallel. How come? How come they're not parallel?
Is that different slopes?
Different slopes. So as a result, they must intersect at some point. Now, the intersection is the solution to both equations. What that means, what's interesting, remember how in your quiz that you just got back, you gave several solutions to that equation? You could find an infinite amount of solutions for a given single equation. But when there's two lines intersecting, there's only one solution that satisfies both equations. That's the intersection itself. So a solution to both equations is the intersection of the lines. Okay, that's what we're talking about right up here. Any ordered pair that satisfies both equations is the solution. That is where the intersection itself is. So if I wanted to figure out what x and y is to solve this, it also satisfies this, it's that intersection right there. Now, if the two lines are parallel to one another, yeah.
I should probably ask a question when you finish it.
Okay, so hold on 1 second, that's fine. Look at the third scenario on the far right. When the lines are parallel to one another, are they ever going to intersect? So therefore, they will never have a solution. There's no solution to this system because they will never intersect. What about here? When the lines are the same, how many solutions do you have then? Yeah, an infinite amount of solutions. Because every point on one line has to be on the other line if they're the same. So when lines are the same, you have an infinite amount of solutions. When the lines are parallel, you have no solutions. When the lines intersect once, you have one solution. Let's extrapolate this idea. Okay, we're not going to do this in this section specifically, okay, but what if, and we're going to do this later in the year, if I have a parabola and a linear function, how many solutions do I have now? Two. Well, what if that linear function actually instead looks like this? Oops. Like that. That's actually good. Now how many solutions? 0, because there's no what? Okay, and then finally, what about this? Then there would be, everybody, how many solutions? Just one. So, maybe more than one, but let's assume that that is a point of tangency. Okay? So if this point is tangent here, then there'd be one solution, two solutions, or as the blue line shows, 0. So for linear equations, like we saw a moment ago, right? For linear systems, It's either one solution, no solution, or infinite solutions. That's all it could be. But the minute you get to parabolas and other shapes, there could be many solutions. A trig function, this is really cool stuff. You'll learn this in pre-calc. A trig function looks like this. It's sinusoidal. It's a wave. Well, if you have a horizontal line, you're going to have how many solutions? Infinite, because it goes on forever. A sine function goes on forever and ever. Every time it crosses is another solution. So if you had a horizontal line, you would literally have an infinite amount of solutions there. Okay, so a solution to two equations is the intersection of those two lines. Okay, or curves, if you will. But you still have a question, Ego? You said you might have a question after I continue explaining.
Yeah, well, it's two questions.
Shoot.
It's the equation of a parabola, so
Okay.
I don't get confused, is the x distributed to like,
X is squared, the parabola.
Okay.
Remember x squared is parabola.
because like I'm
Or x, parentheses, x plus 1, because technically you distribute that, it becomes x squared.
I'm confusing it with like physics.
No, in physics you still have t squared, like you might have y equals vit plus 1 half a t squared, so t is your independent variable, and it would still be a parabola. It would still be parabolic.
For functions, it's the one where you can subtract both equations from each other, right?
That's what we're doing now, this is systems. So for systems you can do like equation 1 minus equation 2. Yep. It's called, those are linear combinations. We're going to do that today. So before we get to the linear combinations that you were just mentioning, Inigo, here we're going to solve it a different way. So take a look at this. You've got two different equations. But the first one is conveniently solved for y. It's very convenient. Why is that convenient? Why is it convenient that it's solved for y already? Morgan?
Because y is alone.
Yeah, y is alone. What does that mean? What can we do with it, Morgan? Yeah, and a lot of you have seen this. We call this substitution method. Okay, substitution. So you take this expression here. Remember, it's an expression, 2x plus 4. And the expression 2x plus 4 is equal to y. That is going to go in for y in the second equation, right there. So whenever one of the variables, you should probably write this little note down. Whenever one of the variables is solved for, use substitution method. Whenever one of the variables is solved for, use substitution method. So we go ahead and plug that in. Okay, we take the 2x plus 4 and substitute it in for y. Why do we do that? Why do we do that? What does it do to our setup, Inigo?
Well, you can always solve an equation that has one variable.
Yeah, exactly. This equation only has one variable in it now. X is the only variable. One variable, one equation. Go ahead and solve it. Okay, distribute that 2, please. Don't forget to distribute. It's a negative 2 that you're distributing there. Check your answer with mine, please. You should have gotten x equals 3. If you didn't, take a look up and make sure you check through your steps to see what went wrong along the way, if anything. All right, so I solved the equation. I'm done, right? I solved an equation. Whenever we solve an equation, we're usually done. X is 3. X is 3. Benito?
So what you have to do is you have to find the y.
Yeah, we need the y value, right? Because we're looking for a coordinate. Remember, whenever your tests or quizzes say find the coordinate, you need to list an ordered pair. X comma y. So x is 3, Inigo. How do I find y?
So you plug in x to whichever equation you like.
Well, in this case, which is better? Yeah.
Because you have a y isolated, so you just need to do 2 times x plus 4.
Which is?
Which is 10.
Yep. Okay, so again, you could plug x equals 3 into either equation, but it doesn't make any sense to plug it into the second one, because the second one you'd have to resolve for y. So when you plug a 3 into the first equation, you get 2 times 3 plus 4, which is 10. Okay, so your solution will be 3 comma 10. Want to see what it looks like? Okay, there's our answer. These are our two equations we had a moment ago. The bottom one is the equation y equals 2x plus 4. The top one is 3x minus 2y equals negative 11. Where do they meet? They meet somewhere, because they're not parallel. They have to meet somewhere. So they meet and they cross right here at 3, comma 10. Okay, there's my coordinate. This was the answer when we did it algebraically. Do you see the connection, right, between algebraic and graphical? You should be able to solve both ways. So you should be able to practice solving these problems graphically. What does that mean, though? What do you have to be when you're graphing them if it's going to work? You have to be very what? What's the word? If you don't do this, it's going to look all weird. They might not meet up in the right spot. Like, for example, if I sketched this real quick, right, and I did this. Well, I know the bottom one looks like this. The top one looks something like this. And 5 is like, somewhere around here. And, 15 is up here somewhere. And I just drew a sketch. Would I know what the answer is? Probably not, right? So what do I have to do? I have to use several things. Go ahead.
To be precise.
Precise. You need to be precise with it. Absolutely. What else? Use a grid. And your lines need to be made how? With a straight edge.
How do you do that in Notebook? Like, how do you make it straight?
I use my ID card, hold it at an angle, go like that.
Like, I know all papers have like a 90-degree angle and they're all straight.
Yeah, but it's not enough thickness, so use your ID card. Anything that's not metallic. So the ID card's plastic. Just hold it at an angle like this, like at like a 30-degree angle, and just draw right along the ID card. Anything, really. I mean, like this box right here. I can go like this, and have a straight line that goes across. As straight as can be, obviously, right? Because you're going to have some issues with the size, thickness, and stuff. Okay? But if you're given a grid, you should be able to draw a generally straight line because you'll know the slope. Count the slope, up and over, etc., etc. All right, how about example 2? How would we solve this one? And remember, we could solve it the way we did the last one, isolate one of the variables and do it. But let's solve it a different way that maybe some of you know already. What's the other way to solve these systems of equations that you probably learned the basics of last year? At least the basics of. Janet?
I forget what it's called, but like you can subtract one equation from another.
Yeah, so we call that elimination method. The last one was called substitution. Oh, not E-L-I. Oh no, yeah, that's right. My spelling is terrible sometimes. Elimination method. Why is it called elimination method? Why is it called the elimination method?
Because you eliminate one variable.
Yeah, your goal is to eliminate one of the variables. Right now, this is not very convenient. Because if I just added straight down, I would get 4x plus 9y equals negative 6. See that? If I added straight down, it wouldn't work out very well, would it? So I need coefficients that are opposites of one another for them to cancel. And I teach this, by the way, with always adding. I don't teach it with subtracting. I teach you always going to add the equations together. So you need the variables to have different coefficients. What do you recommend?
Multiply the bottom by 3.
Yeah, multiply the bottom one by negative 3. Why am I saying negative? Because I'm going to add them. If you did 3, you could subtract. That's fine, really. But elimination, the idea is you're always adding rows together. These are rows. Okay, you'll learn, if you take a linear algebra course, if you're into math in college, I took a linear algebra, you do all this with matrices. And I'll show you how to use a matrix at the end. But you do all what are called row combinations. So here's what I'm going to do. I'm going to call this equation 1, and I'm going to call this equation 2. I'm going to take equation 1 and add, okay, and I'm going to add negative 3 times equation 2 to that. This is like my command prompt. This is me telling you what I'm doing. Taking the first equation and adding negative 3 times the second equation to that. So I should probably write that down, right? So the first equation I just have to copy. That's easy. And then negative 3 times the second equation is what?
Negative 3x minus 16y
Equals 21. Very good. Okay, so we can see that Christian knows what he's doing here. Just took negative 3, multiplied by every term in the second equation, and then simply add straight down. Okay, you've thus eliminated the x variable. These cancel. 4y and negative 15y is negative 11y, and this is going to be 22. So y turns out to be conveniently negative 2. I'm not done. I have y, what do I also need always? X. Now in this case, I would plug it into the second equation because x has no coefficient. I'd plug it in right there to make it easier on me. Yielding x plus, and this is 5 times negative 2, which is negative 10. X plus negative 10 equals negative 7. How do I get rid of a negative 10? I add 10 to the other side. Okay, if you want to write this like this, if it makes it easier for you to write it like that, that's fine. Either way, you got to add 10 over. So x is going to equal 3. So the answer for this one is 3 comma negative 2. Okay, that's our final answer here, bubbled in. 3, negative 2. Again, listed as an ordered pair. How do you check this, that you're right? How do you check it on the test?
You can just follow what y and x is into substituting in.
You can substitute it right in, very good, into both equations to see that you're right. What else would you do? What else would you do? Graph them. Graph them both, but to graph them, you got to solve for y, so sometimes more work, right? I'm going to teach you toward the end of this lesson how to do with what's called a matrix on your calculator, and you can check it in like maybe 10 seconds it takes, literally. Okay? It's a really cool method. So I'll show you how to do that at some point in this lesson. Example 3. Now, why do you think I gave you parts A and B here? What do I want you to do? Identify what?
Which one needs substitution and which one needs,
Elimination. Very good. Okay, so on your own, go ahead and do these. Go ahead and practice these on your own. Identify which one you're going to use where. One makes more sense than the other. Okay, try it on your own, see how you do. When you're done with part A, just look up. When you finish part A, take an idea, look up. What's going on with part A? We could explain this result again, Morgan?
There's no solution.
Why not, Morgan?
Because B is not equal to 1.
8 is definitely not equal to 1. It's a contradiction, so clearly there's no solution. Who can tell me physically why there's no solution?
The lines are parallel.
The lines are separate from one another and parallel. How do I know they're parallel? If I solve for the first one for y, I will get a slope of negative 1/2. Look at this in standard form, negative a over b, right? So they have the same slopes, so they're definitely parallel. If they have the same slope, they could be the same line. They'd be on top of each other. But in this case, if you solve the first one for y, you're going to end up getting negative 1/2 x plus 1/2. So your y-intercept would be 1/2, so they would be staggered a little bit. Okay, both slopes would be negative. So these are parallel lines. There is no solution. Please try to get used to this idea of commands. I know it seems tedious and annoying, but trust me, in college you will think back and say, oh, Mr. Howard, thank you so much. Because you will use this idea, this concept of writing out your commands. When you're doing what are called row reductions, you're going to literally have to write down row 3 times 2 plus row 1, replace row 4 in that spot. And you'll see what I mean when we get to a matrix rows, but these are like rows. So use these commands so you know what to do.
What is 2 times 1?
So 2 times equation 1 plus equation 2. So double equation 1. I'm stating what I'm doing. I'm doubling that first so that I get negative 6x plus 10y equals negative 12. I did that because I saw that there was a 6x here, right? And I want this to be the opposite of it. So if I double everything in here, I get the opposite of it now. So double equation 1 plus equation 2. What happens though? Everybody, what happens? Yeah, giving you what? 0 equals 0. Isn't that true? That's definitely true. So what could you say about this? Instead of no solution, infinite solutions are all real numbers like we've been talking about. Okay, infinite solutions. Okay, infinite solutions. If all your variables drop off and you get a contradiction, as we saw in chapter 1, there was no solution, still no solution, the lines are parallel. Infinite solutions means those lines are what? It's the same line. It's the exact same line. Okay, two lines that lie on top of one another intersect infinitely. So, at example 4 here, we've got the statement that if 3x is equal to y plus 5, then 2y minus 12 is equal to, 2y minus 2 is equal to 12k, solve for x in terms of k. This is a really traditional problem that a lot of people haven't seen before or don't not always do right away. So you need to really make sure you're focused in right now because this is definitely something that's probably either new to you or if you've seen it, you're probably not a pro with this just yet. So first of all, for someone who thinks they know about this problem a little bit, what does it mean when it says solve for x in terms of k? Solve for x in terms of k. Let's focus up, guys. Make sure we're all focusing on this. Yeah, Nico.
It means that since you can't really solve for x, you have two variables, you should just isolate that.
Isolate x, good. So you see solve for x, you're just going to isolate x. You can't really get a number for it where you see y. What does in terms of k mean though?
That, like, you should do x equals whatever, and then k should be on the other side of the equation. Like k should, if you know k, you know x.
Exactly. So k is something that affects the value of x, right? So your answer is going to be like this. X equals 2k plus 7. Or x equals 3k squared. Or x equals k over 2, right? So k is in the expression for x's value, really. So if you know k, as Amigo said, you know x. So we're going to solve for x, but our answer is going to have the variable k in the answer for x. So it's not going to be simply a numerical quantity for x. So you might say that x is a function of k. X's value changes based on the value of k. So let's see how we can do that. We'll look at the first equation. In the first equation we have 3x equals y plus 5. In the second one we have 2y minus 2 equals 12k. But in neither equation do we have x and k. Right? This is not in both equations. X is in this one and k is in this one. That's the problem we have right now. So there's no really linking factor. But I noticed there's something else in both equations. What else is in both equations, Alex? Y. Y is there. Y is here and y is here. So in physics, you're going to learn in 2 years from now that you call this a linking variable. It links the two equations together. It's the one thing that they share in common. Okay, you might want to write that if you want to call it that now, you can. Okay, but y is in both equations, so it links them together. So if we could solve for an expression for y in one of the equations, we could always substitute it into the other. So this is all substitution method. This is not elimination method here. It's substitution method, but strictly with all variables. So, Christian, help me out. If I solve for y in the first equation up here, what does it become when I solve for y?
Negative y equals negative 3x plus.
It will give me positives, right? Instead of negative y.
So y equals 3x minus 5.
Yeah, there we go. Okay, so subtract 5 from both sides. That becomes y equals 3x minus 5. And that's definitely true. And we can then plug that into the second equation. And then we'll get everything with x and k together. So let's take this expression right here. And again, you can do this more than one way. You could have solved for y in this equation and plugged it into this equation instead. Either way works. Okay, try it the other way, that's fine. You'll get the same answer. So if you tried it the other way, keep going, don't stop. So take this quantity, plug it in for y right here in this equation. So I'm going to have 2 times that whole quantity minus 2 equals 12k. I'm going to take this expression that I'm circling in red right now and rewrite it in red over here. So I've performed an operation that has now eliminated a variable, right? It has eliminated the variable y from both of our equations. We've come up with a combination of the first 2 equations and made a third new equation. And now we have to solve that new equation for what variable? What do I have to now solve this equation for? For x. Very good, James. It says solve for x in terms of k. So our answer will definitely have k in it. So let's go ahead and first start by distributing. Okay, we could distribute first. I mean, actually, we really don't need to distribute first. We could add the 2 and then divide by 2 to get rid of it. It doesn't matter. What do you guys want to do? What do you feel more comfortable doing? Distribute. I think most people would distribute, so I'll do that first, but you don't have to. You can move this 2 over by adding it, and then divide by this 2 if you wanted to as well. But let's distribute because that does seem better anyway. So we distribute this, it becomes 6x minus 10 minus 2 equals 12k. The minus 10 and the minus 2 is a negative 12. I want to add it over. So how do I add over? So I'm going to add a positive 12 over here to get rid of these 2. Add 12. Then the next line I can divide by 6. I can divide everything by 6 now. If I recall, that means when I divide a binomial by a monomial, I divide it into both terms. Oops, I don't need the fraction line anymore. Okay, so divide this first. 12k over 6 is simply 2k, and then 12 over 6 is simply 2. And there's our final answer. And as Inigo mentioned earlier, if you know k, you know x. So this might be part A of one of your problems. And then I might say, given now that the value of k is equal to 2, determine the value of x. Well, you don't go back to the beginning and redo all this. You just literally plug that in here, and you can get the value of x as a result. Okay? Questions on this? Do you see how it's an application of the substitution method? Does that make sense? Okay, not elimination really. I mean, you are technically eliminating a variable, but by using substitution. Okay. Solve the following system of equations algebraically. Take a look at this one now. What do you notice in this case? How does this differ from what we did before with 3 equations and what we remember them with elimination? What's the only difference? Yeah, there's 3 variables, so as a result, how many equations are there? 3 equations. Remember, number of variables has to match the number of equations. So, we think about elimination method here now. Show of hands real quick, how many people have done this with 3 variables? With 3 variables, anyone done this? Okay? Alright, let's have an idea. So we think about elimination method, and the problem is, no matter what I do, I can't eliminate enough to solve for a variable on the first step. So I have to perform several steps before I can then combine those several steps into one. So what variable do I maybe want to get rid of? Look at the coefficients. Look for a coefficient where the coefficients are like in some sort of a balance, where you might see like a 2 or a negative 2, or 7 or negative 7, where you might see like one where like, it has a 2 and then a 1. It's very easy to match those up. Remember, we want to have opposite coefficients really to combine those rows. Which variable looks like it's the easiest to work with? I could see 2 choices as being easy to work with. One of them might be a little bit of a headache. 2 that should be pretty easy. X? Yeah, see how x has a negative x in equation 2 and a positive x in equation 3? You can see already that if you added equation 2 and 3 together, what would happen to x? It would cancel out and go away. So I would work with eliminating x first, which will leave you with y and z. But that's 2 variables, isn't it? So you need to do that again to eliminate x a second time with a different combination of rows to get another equation with y and z. Then you have 2 equations with y and z. And then you can do elimination of those 2 to get either z or y. So we're going to break this down a little step at a time. So let's combine equations 2 and 3. And if you don't understand what I'm saying just yet, just watch for a moment. It might be a little more clear. So I'm literally going to rewrite them. I know this is tedious and you don't really have to do it. But a lot of the time you alter the equation, like you double one of the equations or something. So I always end up writing them out anyway. So I'm going to do it just so you can all see what I'm doing here. Now I'm literally going to add straight down and come up with a new equation. These cancel, so there's no x's left. There's 6 y's here. There are negative 10 z's. And there's a total of 4 on the right. So I'm literally adding straight down. Okay? Incorporating the signs. Now, this is a new equation, so what might I call this equation? We have 1, 2, and 3. What should we call this equation? What should I call it? 4. Okay, let's call this equation 4. Because we're going to have to use equation 4 in a little bit. Now, I got rid of x once already. And I came up with this new equation. How did I get rid of x? I got rid of x using equations 2 and 3. So we cannot use those equations together again. Is that clear? So now we can either use 1 and 3 together, or 1 and 2. What would you prefer? Using 1 and 2 together, or using 1 and 3? And it honestly doesn't matter. Both ways work. So it doesn't matter. 1 and 2 together, or 1 and 3 together. Either way works. Will, I saw your hand. 1 and 2. I would agree with Will because of the opposite signs. And all I have to do is multiply the second equation here. If I multiply everything by 2, it'll make this coefficient right here a negative 2x, which will cancel with this positive 2x. So I would agree to combine equations 1 and 2. How will I do that? I'll take equation 1, and I'll add double equation 2 to it. So I'm going to write that out. Equation 1 plus double equation 2. This is, remember, my command. So I'm going to rewrite equation 1. 2, negative 1, 2, negative 7. 2, negative 1. Is it 2, negative 7 or negative 2? 2 or negative 7. And then I'm going to double equation 2. So that's going to be negative 2, 4, negative 8, 10. Negative 2, 4, negative 8, and 10. I'm just remembering the numbers so I can recopy it down easy. Let's see if I did that right. Good. 4. 2. Okay. So at this point in time, we can add straight down again. What do we get as a result when you add straight down here? What do you get when you add straight down, Jeff? Yeah. And clearly, Jeff, isn't that a different equation? So let's call that 5 now. Because a moment ago, we had a new equation. We called that 4. Let's call that 5. And now what we can do is we can write equations 4 and 5 together. Let's take a look at those together now. There's equation 4 at the top, and there's equation 5. Let's write them together on the right over here. So I've got 6y minus 10z equals 4. And I've got 3y minus 6z equals 3. Now, it's not easy to work with z, but you could. You could make them both 30 and negative 30, right? If you want to eliminate z, you could get them to equal 30. Multiply the top one by 3, multiply the bottom one by negative 5, that would be positive 30. But it makes more sense to eliminate y, doesn't it? It makes more sense. Christian, how would I eliminate y in this case? What could I do with these two equations here?
You can multiply the bottom by 2.
By not 2, but close. If I want to add them together, I need it to be the opposite sign, so
Oh,
negative 2. So let's take equation 4 and add negative 2 times equation 5 to that, which is really, again, subtraction. So a lot of you have done this with subtraction. That is fine. You can do that. I always do it with row combinations. I think of adding. So equation 4 is here. And I'm going to double the second one and negate all the signs. Okay, so remembering literally to double all these, 3 becomes 6, 6 is 12, 3 is 6, and positive, negative is now negative, positive, negative. Add those together. Y's cancel. I get 2 z's left over, and I get a negative 2. So what's z, everybody? Yeah. Okay, z is going to be negative 1. And if z is negative 1, you could take that value and plug it into either 4 or 5, either here or, oh, that should be a z, that was a typo, sorry. Either there or there, plug it in for z, negative 1. What do you get for y? If you plug in z as negative 1 there, what do you end up getting for y? Jeff, did you get it already? What did you get for y? -1 also? Did others get -1 as well for y? I just want confirmation from others. Okay. All right, so when you plug that z value in, you get y equals -1. Well, how do you get that? You take the -1 here and literally plug it in for z right here, and then just solve for that y value right there. And if you get z and y are -1, you go back to the beginning of the problem. Go back to where we had everything in the beginning here. We take a look at our original equations now. If z and y are -1, which of these equations makes the most sense to plug into? There is one that is the best, for sure. Which one of these is the best to plug in for z and y so that I can get x? Which one makes the most sense? Come on. Least steps possible means use which equation?
1,
Not equation 1.
2,
Not equation 2.
3.
Why 3? You can explain.
X doesn't have any code.
Look at x. What's the coefficient? Are you trying to find out x still? So why not plug these in, just move them over, you got x.
Yeah.
You don't have to worry about the negative or the 2, so go wherever there's no coefficient. Okay, so these are both -1 here, and here is -1, and this is a -6, this is a +4, this is your x, equals -1. Makes this 6, makes this -4, and there's your x. That's going to yield +2, which we're going to subtract. Tell me this is also -1. +1. Oh yeah, +1. I didn't catch. There we go. I got to carry it on my side. Okay, this is going to yield a +2. So no, it's going to be -3. Right? -3. Because this is going to become a +2, and then I subtract that from -1 is -3. So what's my final answer as a coordinate? How about I list this coordinate? There's 3 parts, x, y, and z, so no different than an xy coordinate. How would you list an xy coordinate as an answer? M?
This is just like x, y, so -3, -1, -1.
Very good. Okay? That's a 1 at the end, not a 7. -3, -1, -1. Okay? So the idea behind 3 variables and 3 equations is that it's really elimination method, but you do it several times. So you eliminate twice to give you 2 variables and 2 equations, and then you eliminate once to get the last variable. Once you get one variable, you can get all the rest. You don't have to do elimination again. Is that clear? I can't tell you how many people do that. They do all the elimination to get like z first, like we did, and then redo it again to get y. No, just plug in to get y, and then plug y and z in to get x. Now, I'm going to go to your calculators now, so please take out your calculators. We're going to utilize this equation that's on the board, but I'm going to pull up, I'm going to pull up my computer so you can see the calculator interface. Say again?
We're gonna use the second equation.
I can't hear you.
We're gonna use the second equation.
We're going to use these 3 equations all together, I'm saying. This set of equations, All right, so everybody can see what I'm doing on the board. Take a look up. Again, guys, remember, if you're watching the video at home, you're not going to see this because you're seeing what's on the iPad screen. It doesn't actually record this. So what we're going to do is we're going to take a look at a matrix, and it's a matrix method. And it's a method of taking a system of equations and rewriting it in a table format. So look at the equations we have on the board. 2x minus y plus 2z equals -7. Just look at the coefficients. What would the coefficients be? List them in order. List them in order. James, what are the coefficients right across the way?
2,
And the last part? Yeah. So literally, the coefficients of each one are going to be like the placeholders in your matrix. You're going to place those numbers in table format, where you're going to have 3 rows and 4 columns. Can you visualize the 4 columns right now? X, Y, Z, and then your constants on the other side. This is technically called, on the right-hand side here, This is technically called what's called like your constant vector, and this is your coefficient matrix. You're going to learn about that, in some form of a math class in college or a linear algebra class, or if you do go into engineering, you'll see about this with a matrix. It's really useful. So what we're going to do is we're going to write a matrix with those numbers. So what we can do, and I'll show you to the right here, is literally just take them, and we're going to place 4 columns and 3 rows, and just write out the numbers. Okay, so go ahead and write these out, please. And you're going to write them down for a certain reason, because you're going to write down the result afterward also. So this is what our coefficient matrix would look like for the entire thing, including the constants on the right-hand side. And there's more than one way to solve something like this. You could use your constant vector, and then you could use your coefficient matrix and divide it by using the inverse of that matrix. I'm going to show you a way that's called a row reduced form, and it's a simple command in your calculator. And all you're going to do now is use it to check. And what it's going to do is it's going to do elimination for you. Okay? It'll take all the stuff you did with elimination and do it for you on the calculator. If you take linear algebra, you'll learn that you can actually do this with the rows. You could say, like, take row 3 and row 2 and add them together. What would happen when you add row 3 and row 2 together? Don't you get a 0 here? Isn't that what we did in the beginning? Didn't we take equation 2 and equation 3 and add them? It's the same thing that I'm teaching with those commands. You would do with this. You'd write R2 plus R3 replaces R3. And you'd have a new equation as a result. Until eventually you get a vector or a matrix that looks like this. This is what the eventual thing will look like if you do operations on it. And these will all be numbers. That's your goal with row. It's called row reduced echelon form. The rows are these. They're reduced so that they have 1s and 0s. It's echelon form, meaning there's 1s along the diagonals here. 0s everywhere else. That's like what it's termed. You don't need to really know that too much, but know what you're doing. This is what your calculator is doing. It's adding rows together more and more until you get enough zeros. So if you add these 2 rows, you end up with a 0 here. You can replace that in this row, which puts a 0 there. Then you want to add these 2 rows together to get a 0 here. And if you have like 7x and a 5, or 7 here and a 5 here, you can divide by 7 and get rid of it. So your goal will be to eventually get zeros in those spots. We're going to do it on the calculator. So let's take a look at our calculator now. Press, please. See this command that says matrix? It's the second function for this button. I'm pointing to it on the board right now. So press second, and then press the x to the negative 1 command. That'll bring up A, B, C, D, E, all these other names. Now, if you want to operate on a matrix, you're going to simply use this command, A, B, C, D, whichever one it is that you're using. But we have to fill up our matrix with numbers first. Remember, I'm going back now. We need to put these numbers in. Okay, see these numbers I'm pointing to right here? We're going to put these numbers into a matrix and then perform this operation that we would do by hand on the calculator, come up with this.
Matrix and
So all you're pressing right now is second and then the x to the negative 1 command, which is matrix pretty much. Okay, and you're going to have what shows up on my screen on yours. Go over to edit. Hit enter on matrix A. Now, the way matrices are formed are rows by columns, always. And I remembered it, this is really bad, but RC, like RC control bar, radio control. When I was a kid, I liked RC cars or like different things that you would be able to control with like some sort of a joystick of sorts. Now it's obviously a touch screen and stuff, so I'm trying to go back. So RC, okay, rows, then columns always. And if you do it wrong, it won't look right. So press 3 because there's 3 rows, and then 4 because there's 4 columns, and just hit enter after each. It looks like there's no 4th column, but the screen continues to the right. That's what the dash means. The dash means there's another column. It can't fit as many columns as you put. It's not going to make the pixels tiny. So if you press to the right, you can see that you can go over further. Okay, all the way to the far right. So we need to enter these numbers, and those numbers are here. So we're going to enter 2, and then press the enter key. Okay, so I'm doing this. You have it on your screen also. 2, enter. The negative command is down here, below the number 3. So negative 1, enter. 2, enter. Negative 7, enter. So I've entered the first row. I'm literally entering the numbers that we have on, it's on your iPad if you can't see what I'm putting up here. Okay, then negative 1, enter. 2, enter. Negative 4, and then 5. Finally, 1, 4, negative 6, negative 1. And as long as I didn't type anything wrong, the answer will be correct. But if you type something wrong and your answer does not seem reasonable at all, please don't be like, my calculator told me so. It's like the worst thing here. Okay, your calculator can be wrong if you put stuff in that is wrong. My teacher used to say, garbage in is garbage out. If you put the wrong thing in the calculator, you're not going to get the right answer. Now, you've entered the information into your matrix. Press second, and then quit to go back to the home screen. It's mode, the button right next to quit. Press second, and then hit mode. It'll quit out of that. Second, and then mode to quit out. Anything else?
Yeah, there's no.
Right next to the second.
Oh.
There you go. Then you're on the bottom of this, okay? Now, we're going to then go ahead and we're going to press second, go back into the matrix. Into the matrix. Any Matrix fans here? The movie? Nobody? It's way before your time, isn't it? If anyone likes sci-fi movies and stuff, or is it like computers, The Matrix? Awesome trilogy. Anyway, so we want to take a look at Matrix A, which we've now created. See, it says 3 times 4? It means 3 by 4. That's what we typed in earlier. That's the matrix we entered. But we need to perform some mathematical operations. So go over to math. We're going to do what's called a row reduced echelon form. It's under RREF. Should be letter B. Okay, see RREF, not just ref. RREF. Hit enter. It'll bring that command up on your home screen. Go back to your matrix. And now we want to call out matrix A, not edit it. So just enter on matrix A to call it out. You don't really need to close the parentheses, but I'm going to be safe. And I'm going to hit enter and take a look. We don't get what we got before. Why did that happen? What did I type in? Thank you. Nobody stopped me. You guys got to stop me. Thanks, James. I put in 6 instead of -6 at the end. Yep, there it is. See, and what did I say? Garbage in, garbage out? And I am the prime evidence of that right there. And that should be -1 here, right? So I switched up my negatives there. They should both be negative. Dang. Now, fun fact, take a look. If you screwed up like I did, and you embarrassed yourself, you want to do it quickly, press second and hit enter. It'll bring up the same command. You don't have to do it again. Press second, hit enter. It always brings up the last command you typed in.
What do we do after we do RREF?
So then go press second, matrix again, hit enter on matrix A. It'll bring it out to the home screen, and then hit enter. Still didn't work though. Did I put another mistake in?
No, I'm getting
Maybe. No,
Are you getting what I'm getting or no?
No.
You are? But you're not. What did I type wrong, guys? This is embarrassing now.
Oh, you mean the second
Maybe
one,
the
the decimal?
bottom right number, whatever you put there.
Let me just run through them real quick. We've got 2, -1, 2, and then it should be -7.
It's the -4.
Oh my lord.
4
Right here?
Yeah.
Jesus. How embarrassing is this? Yeah. Wow. Alright. 3rd time's the charm. 3 strikes and you're out. There it is. Okay? -3, 1, 1. As I wanted to say, the same exact answers as we got by doing it by hand. So if you want to check this on your calculator on the test, you can. Now, on the test, here's what I'm going to do. Listen to this carefully so you know that you do it right. I'm going to make you do some of these by hand on the test. But when I give you word problems at the end of the test, which we're going to see, word problems for these, I'm going to allow you to set up all the equations and solve the word problems by the matrix method. Does that make sense? So please don't do the word problems by hand. Set them up, write out the 3 equations you're going to utilize, but then please use the matrix to solve them quickly. Let's take a look at now an example of one of those. What happened to our last